Also, okay, everyone. So today we are hosting Tayfun. Actually, Tayfun is my former student from Hacettepe University, and I still co-advise him with Erkut. And today he will talk about his master thesis, which brings many different domains into a single pot, including computer vision, natural language processing, and a little bit of cognitive science. And we have just recently presented this work in one of the workshops in NeurIPS called Shared Visual Representation in Human and Machine Intelligence. And in that sense, this talk will be a little bit like a continuation of our last talk, which is also in a similar direction. Welcome, Tayfun, and the stage is yours.
Thank you for the introduction. My name is Tayfun, and today I will be presenting our recent work on a new visual question answering benchmark, which we call as CRAFT. It requires deep causal and temporal reasoning and deep physics understanding. The work actually spans 2 universities and encapsulating 3 different research laboratories. Before going to details of my presentation, I would like to talk a little bit about myself. I took my bachelor degree from Middle East Technical University, Computer Engineering Department. And 3 years later, I joined the Hacettepe University Computer Vision Laboratory to obtain my master's. And hopefully I will take it in the next month, I suppose. And concurrently, I'm also working as a graphic software developer at Pixary. Here is the overview of my presentation. Firstly, I will introduce the problem that we are working on and talking a little bit about the related work as well. Then I will continue the data set that we have created and the experiments conducted on CRAFT, and then I will conclude my presentation. As you may all know, the artificial neural networks had started to be used in deep learning systems a lot, and they have achieved a great success in the recent years in the research areas that are in the slide. These are just examples, for example, image classification or text translation. And we have also seen example models that beats professional Go players as well. Although these are great successes, there are some missing parts in those AI systems as well. For example, one of them is the common sense knowledge, which is shared by most of the people. It is actually at the basic level of practical knowledge and reasoning, and it concerns everyday situation and the events. And we gain such capabilities starting from birth, and we experience the environment and gain common sense knowledge. And for example, while you are watching this video, you can estimate the different force dynamic between different objects, dynamic objects, and you can reason about the causal and temporal structures that are for the events that are occurring, and you can answer the questions like when, why, or the counterfactual questions like what if, and you can simulate in your head the counterfactual simulations. For example, what if I remove this object? What happens to this one? Such thing, you can visualize them. But you do this all by approximate estimations. You do not take pen or a calculator to accurately estimate Newtonian physics or so. You do not do that. You just estimate approximately. This capability of yours is known as intuitive physics, the understanding the environment and making approximate predictions about the events that are happening. This is known as intuitive physics in cognitive science. And the question here is that are the current AI systems have such capabilities to understand their environments and making approximate predictions about the events that are happening. We are actually working on answering such questions. In the recent years, studies on visual question answering have been proposed. They are actually the starting point of the understanding the reasoning capabilities of the AI systems. Initial works actually used original real-world images and real-world videos, but they were not scalable, as you may guess. And they also suffer from a serious problem because they are real-world. They do not have the uniform answer distributions, and neural networks started to cheat while predicting the answer. They didn't understand the content inside the video or the question. They just search for the most common answer type for a question. For example, if the question is a counting question, they return 2 as an example and received 70 or 80% of accuracies. And this is a huge problem when you want to create a VQA data set. And researchers then to solve this problem started to work on more controlled environments such as Clever. It is actually using a Blender tool to create its scenes and create questions automatically by using some NLP scripts to be actually working on more controlled environments. But actually we inspired from Clever a lot, but it actually contains a single static scene where there is no motion or no physics in it. And the questions required only spatial reasoning, no temporal or causal reasoning was required to answer Clever questions. And for the physics reasoning, in the recent years, FIRE and tools benchmark have been created to improve causal and temporal reasonings as well. In those works, there were multiple scene layouts in 2 dimensions, and the task, the benchmark asks agents from agents to complete 1 or more actions to complete the task associated with the scene. But those works, the language component in those works was largely missing. Actually the language is actually an important core concept in human cognition as well. More closely to our work, Clever has been proposed. While we were also working this project, Clever has been proposed. There were 4 different question categories: predictive, explanatory, counterfactual, and descriptive question categories. We also inspired this work from this work a lot, but they used a single scene layout and they used a single action, which is collision, which makes the questions and the scenes a little bit boring, because the questions were all about collision between 2 objects, and we wanted to extend this in our work as well. We extend this work by inspiring from the recent developments in cognitive science. We added new question categories such as cause, enable, prevent, which are known to be in the core of representing causal relations. We represent these relations between different entities, which are effector and the patient. For example, in our questions, there are questions like, if we ask if a effector enables a patient to do a task or so. This was new, we added in Craft, and we will see the examples of them. We actually acquired the descriptive and counterfactual question categories and append these new question categories. Therefore, Craft has a total of 5 different question categories. And we have designed Craft to be intuitive for humans, but challenging for the AI systems. And the current version of Graph has nearly 38K question video pairs from 30K videos. We are also working on extending this data set version 2 as well. We extracted 10 seconds videos whose resolutions are 256 by 256. And we used BoxDD, which is a very famous 2D game simulator, to create our videos. We created 10 different scene layouts consisting of different static objects. We have different static objects like ramp, platform, basket, left and right walls, and the ground. In our simulations, we draw all these static objects in black, and we use a single size for them. While creating a single video, we actually randomly select the attributes of these static objects, for example, such as position and orientation, and we keep them fixed throughout a single video. And they created the scene layout like that. Other than the static objects, we have also dynamic objects. We use 3 different shapes for dynamic objects, which are cube, triangle, and circle. We use 8 different colors that we have obtained from the Clever, original Clever work. We use 2 different sizes. Although these are fixed properties, static properties, the other properties such as, for example, linear velocity or angular velocity are in constant change throughout a single video sequence, 10-second video sequence, until they rest if they. Other than the scene elements, we also want to find the answer to the questions automatically. We create a question for Craft and we find the answer automatically. To do that, we have to formally represent the simulation, the video and the question. To represent the video, we use 3 different structures. We extract all attributes of the objects at the start of the simulation and at the end of the simulation. And we extract events and create a causal graph from the events. And these 3 structures actually are enough for any model to or any code to find the answer to the question. We actually want AI models to estimate these 3 structures. I don't know how they do that. There are several events in our simulations other than start and the end events, which are actually the basic events that represent the start and the end of the simulations. We have the following events. We have collision between 2 different objects. We have touch start, where the objects do not collide, but they start touching. We have touch end event, and when an object enters a basket, we have also extract an in basket event. And we use functional programs to find the answers to the questions. I mentioned the 3 different structures before. By using them, we actually extract the answer to the question. These functional programs consist of different functional modules. These functional modules are actually look like the programming functions in the programming language. They have multiple input types and they have a single output type. They create a functional program in Craft. We have functional programs associated with a task in Craft, associated with a question, and they actually tells us the basic reasoning operations to answer a single question. We also provide those functional programs with our data set for further use as well. The AI models may prefer or may not prefer to use them while training their models. They can be used to improve the model as a different signal as well other than the question and the visual, the video. The list is the input and output types of our functional models. We extend the clever by adding event or event-like, event set list types, data types. Here is the different functional models that we use. These are the input and output functional models. For example, for the input one, we have scene at start and scene at. For example, we have events. This is the causal graph that we created from the simulation. We have also output functional types. For example, if we have a counting question, it must end with a count functional module. We have also exist and query-like functional models. The input and output types are written as well. We have, similar to Clever, we have functional models that are working on objects or object sets, which helps us to filter object sets to, for example, if we want to objects that are in motion, we may able to use them. We have also event functional models. This is actually contains the functional models that we have proposed on Clever. We are using different event functional models. For example, we may filter the events which are actually consisting of ground collisions. And we have also some auxiliary functional models that contain, for example, sets operations such as intersects or difference. As I said before, we have 5 different question categories. We have a total of 65 different tasks. This one is the first one, the descriptive task. It actually requires, for example, counting questions and some temporal analysis as well. Here, for example, the question is how many objects fall to the ground. The below part is the functional program associated with the question. In order to answer that question, you find the actually you may use the functional program to find the answer automatically. We are also using counterfactual questions. This one is very similar to what is in the Cleverer. We provide counterfactual situations by removing an object. For example, how many objects fall to the ground if the small yellow box is removed. Other than this, and we provide an extension by requiring multiple counterfactual simulation as well. For example, we can ask, does the small gray box enter the basket if any one of the object is removed? The model has to simulate the counterfactual video multiple times to be able to answer that question. This one is new and it doesn't belong what is in the Cleverer. The new one, we have the cause tasks. We propose the cause task. It requires understanding whether an object is causing an event by comparing the counterfactual video and the original video. In this one, in the counterfactual video, the model should only look at the counterfactual video, but in the cause, the model must compare the original video and the counterfactual video. And here I pinned the counterfactual event filter functional model in the functional program. Similar to cause tasks, we have also enable tasks, which is very similar to cause tasks, but except the fact that an object here must intend to do the task in the question. What is the intention? How we do understand the notion of the intention? If the object has a linear velocity which is greater than 0, then the object is intend to do the task in the question. Then it can be enabled by other object, by other effector objects. This is the core difference between cause and enable task that we have retrieved from the works in cognitive science, and we also prevent us with we ask whether an object is preventing the other object as well. In this one as well, we also look for the intention as well, because an object cannot be prevented if it doesn't intend to do it. Other than that, we extract from our dataset. We also extract some basic statistics. Here, our aim was trying to obtain a dataset whose answers are uniformly distributed. In Clever or Cleverer, there were only single scene layout. There were no variation in the visual dimension. In the Five-Ray and tools, there were no NLP questions or similar type. There were no NLP in it. Therefore, here the problem for us was a little bit more difficult because we are trying to extend the craft in 2 different dimensions. We have a total of 650 scene layouts and question type pairs. And our scripts are trying to make these pairs to have uniform answer distributions while actually trying to keep the overall distribution as uniform as possible. Actually, we have succeeded to do so far, as you can see from the image. We have also conducted some experiments analysis as well. This is an ongoing work, and these baselines may seem basic for you, but we are also trying to working to create more complex baselines as well. MFA is actually outputs the most frequent answer in our training splits. At MFA outputs the most frequent answer, but it actually knows the question type. For example, it only outputs numbers for counting questions. We have also trained a LSTM, which is a visually blind model. They do not take the videos as input. We trained different LSTM and CNN models, which take the videos as the inputs as well. We have also conducted a small human study as well to see the difference between the performance of the AI models and the performance of the humans. We asked 12 adults to answer craft questions. Here, actually are quantitative results. Although our baselines are very simple, there is a large gap between the human baseline and the most successful AI baseline. And there's a 30% of 30 inaccuracies. And we also look at the difference between different categories, and humans are not able to do well in Causal and enabled tasks. I may say that while conducting this study, we did not provide the information about the difference between Causal and enabled tasks, and therefore they were a little bit difficult for human subjects to identify the difference between Causal and enables. And here are some qualitative results as well. And in the summary, we have provided a new visual question answering benchmark to challenge intuitive physics and causal reasoning capabilities of AI systems. Although our baselines are very simple, in the future, we want to improve them as well. For example, training more object-centric models as well. And we also want to improve our dataset by adding new scene layouts or new question types. And we also want to extend our human study to include more subjects and more questions. And we want also include different types of object attributes such as density. Here we do not have density. They all have the same color and they have same density. For example, using material textures, we can differentiate the objects. For example, we can differentiate a rubber object from a metal object. And we want also add more complex scenes, such as we want to add some chains and ask questions related to different types of objects as well. Thank you for listening to me. If you have any questions, I'm glad to answer them.
Thank you, Tayfun. So, any questions from the audience?
Actually, I have one quick question. So, I mean, like, it's not a question, but maybe a comment. Like, it would be interesting to actually try to understand human perception in situations where the physics is not realistic. So you try to simulate realistic physics, but if the physics doesn't become, at least for some objects, like, what's their understanding of cause and effect relation? That will be very interesting, I think, from my perspective, like, to see how they are responding to those questions. Just a comment, like, because we're always expecting something to be physics-based, but what happens, like, the laws of physics give you results that are unrealistic, at least for some of the objects. How do they, like, perceive that scene? Like, how is their perception changes? That might be interesting. But it's nice work, I think, in general. And I'm not surprised that you couldn't match the human abilities. We also do, like, human experiments. I mean, so, like, one of the things that we observe is there are so many intrinsic behaviors and patterns in force, for example, force signals, that you cannot visually, like, detect that very easily. Like, I can give you a very simple example, like, two people are holding an object and they are pushing towards themselves. So the object is not moving, but there's a large amount of force being applied on the object. So, I mean, like, sometimes having just a visual scene may not give you the right answer. So it's a multimodal thing, right? I mean, like, when we do interact with the environment, it's very highly multimodal. It's not just the visual cues. We use force cues, auditory cues, like sound maybe. If you add a sound, like contact sounds, how does it affect? Like, you have, like, objects sliding, colliding. Like, if you add sounds, how does it affect? Is also interesting question. Like, you mentioned, like, rubber-like objects versus rigid objects. I'm sure their perception may change, for example. These are comments.
Çağatay, I mean, this is a good comment, and also Tayfun, this is a really nice presentation. Related to Çağatay's examples, in fact, I mean, not changing the physics, but maybe changing for example, making the camera upside down can falsify humans easily, and the performance of humans can drop actually below maybe your LSTM architecture. That could be another view of what is going on the field.
Like flat land.
We have received such a comment while we were writing the paper. We actually we cannot use the videos, for example. We just use such visuals to put in the paper. And one of our reviewers said that in our lab, you may want to pin the ground, because the reviewers may not be understanding where the gravity is applied, and we just added the gravity to the original paper. But here, since I'm able to use the videos and it's obvious, and it was a nice comment.
It's even like gravity, like, if the objects have a different gravitational acceleration, like, how would it change? Like, that's very, very interesting. I mean, there are a lot of questions that you can ask in here in terms of cause and effect relation, I think. Like, if, like, you see, like, green object, for example, I'm sorry, the small black cube, if it has a different gravitational acceleration, will that change their perception of the cause and effect relations and things like that. I think a lot of questions can be asked. I think it's very interesting. Lots of potential, I'm thinking.
Yeah, this is actually a new research area that AI research has recently started to touch. There are different types of models, and we are also excited to be working on such physics problem and integrated with AI.
So Tayfun, no, you can.
Yeah, you said that actually. I mean, you present there is a huge gap between humans' performance and what AI accomplish. What are the main drivers of that gap actually? I mean, is it either a representational problem, a model problem, or data problem?
So actually that is related to my question. So Tayfun, just hypothetically speaking, what do you think a perfect AI system would look like if we want to achieve success in these tasks? I think this question is also related to Engin Hoca's question.
Actually, recent works about similar problems are using, for example, the object masks to actually identify the individual objects and integrate those inputs in the model as well. And they have seen that the success, those types of models are more successful to understand the relation between different objects and relations. Other than representing the objects, you must actually ensure for understanding the pairwise relationship. For example, to do that, for example, a graph-centric approach should be more appropriate, but our baselines doesn't include such networks right now. We will be adding them soon, and those are the two main factors that came into my mind, and that may increase the performance of neural baselines. But actually, we also want to improve the performance of humans as well, because we actually provided little information about the scene to see really how they are intuitive. And in my opinion, I would expect a less score from humans, because there are sometimes questions that are not intuitive to me, but the nearly 80% is a good score for our first attempts, I think.
I have a couple comments on Aykut Hoca's and Engin Hoca's questions. First, Engin Hoca mentioned, what is the reason for the gap? One of the main reasons is the baselines were literally that. So we basically created some very, very simple programs or models that we knew were imperfect, mostly to find biases in the data and correct and improve the quality of the data set. So for example, one of the baselines is the language-only baseline. So this language-only baseline doesn't even look at the videos. So if the language-only baseline can answer, let's say, a great percentage of the questions correctly, that doesn't mean it's very smart. That just means that our data set is bad, and we have to go back and actually rebalance the questions and answers to avoid, cheating, or being able to answer questions without actually paying attention to what we want the model to pay attention to. So that has been a big problem since the beginning. So we went over the data set a couple times to rebalance the questions and the answers so that kind of cheating is not possible. And then to Aykut's point and Tayfun's comments, I agree that detecting objects and their relations is absolutely crucial, which we're not really doing in the baselines. But on top of that, I think what makes this task special is the counterfactuals. So the fact that you have to be able to simulate more than one scenario and then make comparisons between them. I don't think any of the existing AI models currently, successfully do this. So if this data set and this study will lead to some new innovation and insight, I think it's going to be in that area.
So in a way, these models should build their own physics simulators just to understand the scene and again evaluate these different possible futures. And Deniz Hocam, I think there are some recent works, especially in robotics, maybe you can also comment on this, Çağatay Hocam, that these models involve the so-called forward models, just from their observations they can just guess how the future will evolve. I think yeah, we should also consider those type of architectures and models in our case too.
Yeah, there are some interesting works like evolutionary robotics kind of thing. Like they just let, like, for example, they built some kind of mechanism, and that mechanism, like by interacting in a physics-based environment, learn to walk, for example, like from scratch kind of thing. So it's just like using the physics of interactions, it is learning to do something. And that's, for me, it's very interesting. I mean, I don't know if you mean those kind of works, but that seems very interesting to me.
So I think in those types of scenarios, there is, people usually use reinforcement learning, but that's reinforcement simply just by rewarding yourself when you can make, I don't know, forward progress and not fall on your face or something. But there is also model-based reinforcement learning where you're trying to model the actual world and its physical rules so that you can imagine possible futures when you make certain moves and what's going to happen, and learn from that without actually attempting to do it yourself. So I think IQ's suggestion was more in sort of being able to model the world without interacting with it, or after just observing it.
But I think Çağatay's Hoca's point is also interesting. So here we are just providing the videos. So in that sense, it doesn't involve any embodiments. But if the model can also like directly make some changes in the environments, and then maybe the learning process could be a little bit more effective.
Yeah, interaction very important. I mean, that's what I'm suggesting. Interaction with the environment is highly important in terms of learning. In terms of that reinforcement point that you made, Deniz, I mean, we've been trying to implement this reinforcement learning with human-robot interaction, and we failed. I need to talk to you guys, because like when you put the human into the loop, it seems very difficult to implement those reinforcement learning algorithms. And also like doing many experiments is impossible, right? Especially like when there is a physical interaction between human and robot. Like you can do like 500 kind of trials to make the model to learn. So I need to talk to you guys about that. This is out of scope of our discussion in here, but I need to talk to you guys about that.
I think Barış is the expert in that stuff.
Yeah, we talked to him a bit, yes.
But yeah, I'm also suffering from reinforcement learning issues right now. One of my students is trying to graduate, and we've been, trying to get this, very, I can't remember the words now, but very finicky algorithm to actually converge to something reasonable. And it turns out it's, reinforcement learning in general is very unstable and difficult to tame compared to supervised learning.
Yeah, I mean, it seems like there's a big gap in that in terms of research wise. Like when human is especially in the loop, like and physically interacting with some objects, something like a robot, or for example, like human behavior is not very predictable. So it's changing from, I mean, even if you repeat, yeah,
check
go ahead.
out offline RL literature. We are doing also some work. I mean, we are trying to basically go over pre-recorded human-human interaction and transfer it to basically human-computer interaction through RL. There are possibilities over there. Nusra,
Okay.
in fact, defend her thesis on a similar topic.
Okay. I mean, so we should talk then. Maybe.
Yeah, Metin and Yücel also has some experience.
Fatma send the link, I guess. Is it related to what we are discussing, Fatma?
Yeah, what Engin just said about offline RL.
Offline game.
There was a
Yeah.
tutorial.
Nice tutorial, and also there is a workshop under NIPS on offline RL.
Ah, okay. This is going to happen, I guess, right? It hasn't
This
happened yet.
happened actually, and videos are online.
Last.
Okay, so I missed that one. Okay, thank you, guys.